All right, here is Chapter 7, Test B that you can use as you're doing your corrections. All right. The first one is just asking you if you know what the difference between a parameter and a statistic. And it says 40% of the trees showed damage. This is the trees from the sample. And remember, samples create statistics. So it's B. Number two, this is just the definition of a sampling distribution. Okay. It is the distribution of all the values taken by all possible samples. We've done this over and over and over in this class, folks. We know there's a true parameter somewhere in the middle, and you take samples, and then you come to the whiteboard, and you put your dots up here on the whiteboard, and what we are creating is sampling distributions. Okay, that is the definition of it. Every dot is a value of a statistic. Every one of these is like an X bar or a p hat. Number three, it is unbiased. Like, how do you know these are unbiased? That is if the mean, let's say this is a mu, is in the center, okay? If the mean or the center of the distribution is in the right place, if it matches the parameter, if it matches mu, okay? And so what I'm drawing here is an unbiased one. All of these dots are X bars, right? All over the place. Some of them are a little above mu, and some of them are below mu, but it's centered correctly. So that's B, okay? These other answers are distracting. Like you're thinking of bias as maybe like a human bias here, like being honest, they're being truthful. That's not what this means. It means the method itself, like taking the numbers randomly and adding them up and getting an average. That method results in a distribution where the center is located at the parameter. 4. Suppose you take a random sample of size 25. So there's n from a population with a mu of 120 and a standard deviation sigma of 15. Your sample has a mean of 115. So this is just your one sample, and your sample had a standard deviation of 13.8. This is a single sample, and this is misleading to people because you almost don't even need this for what they're asking you. It says, which of the following has a mean of 120 and a standard deviation of 3? And it would be this because the mean is that the average X bar will equal mu. Well, that's 120, right? 120. And then the formula on your cheat sheet is that the standard deviation of X bar is sigma over root n, which is 15 over square root of 25, which is 15 over 5, which is 3. So some of these other ones, like the distribution of sample data, that would simply be taking your data from the population. It looks like these numbers are like around 120. So you take a random sample, I'm just making these up, right? You'd have many more than this, dot, dot, dot. If you were just going to make a distribution of this data, you would just be putting a dot for each of these above the number line. You wouldn't be averaging them. You wouldn't be doing anything with them. That is not going to, that's not what we've ever done in this class, first of all. The distribution of the population, that would just be a repeat of this and this. That's not a sample, that's the whole population. So that would have a standard deviation of 15, not of 3. If you had a sampling distribution of the population mean, well, the population mean is 120. So if you only had a distribution of just this, every dot would be at 120. It would have no standard deviation. You'd have your graph and you'd have every single dot right here at 120. Sigma would be 0 for that. Okay, number 5. I'm talking quick because I want to get this done before the bell. This is you're taking a sample size of 25 from a large population. Um, okay. Which is the right statement, right? So if the true proportion is zero point 0.1, then it limit brings you down to, well, all of these, okay? So it's not this, okay? The standard deviation formula is this. This is on your cheat sheet. Always keep this handy. It's right here, okay? And you didn't even have to calculate it, which is kind of nice. You just had to recognize it. Now, is it normal or not normal? It says right here, it violates the condition. It's telling you it is not normal. So you don't even have to really do the work. I mean, you could do zero point 0.1 times 25. That's n times p. It's going to be 2.5. If you don't trust them, you know, um, and it's not going to be big enough. Not bigger than 10. Number 6, the central limit theorem says what? I mean, the light bulb stuff is great. It does say that the population is skewed right, okay? But the central limit theorem says if you have a large number of bulbs in your sample, okay, it will be close to normal. The larger and larger the sample gets, it will get closer and closer to normal, okay? And it doesn't matter that it was skewed to begin with, okay? Um, Look at A. It says as we look at more and more bulbs, so that's good. But it says the average burnout time gets closer to the actual average for all bulbs. That's not true. The average of any size distribution should be centered in the right spot. So it's not A. B, the mean burnout for any number of bulbs has a distribution the same shape, skewed as the distribution for individual bulbs. That is just not true. Um, it is, it's as the original, sorry, if n is small, if sample size is small, it would be skewed. But this is what it's saying. As you get larger numbers of bulbs, the skew goes away. Okay. C is wrong because it's not any number of bulbs that would be normal. It has to be a large number of bulbs. And D says if you have a large number, it will be the same. It will be skewed as the same as the population. That's not true. The skew goes away for a large number of bulbs. Number 7, if you caught on to this, both sample sizes were 500, okay? And we are measuring the heights of people, right? So the standard deviation of x bar is the standard deviation of the population divided by the square root of the sample size. So the standard deviation for Purdue would be the standard deviation of the population divided by the square root of 500. And the standard deviation for, what's the other school? Indiana would be their sigma divided by the square root of 500. And they're pretty much just having you compare these two things. Now, it didn't ever tell you what sigma was for both schools, right? But it says right here, assume the standard deviation of heights in the two populations is the same. So they're saying right here that sigma p and sigma I are equal, which is somewhat reasonable. Do you think the heights of kids that go to Purdue is the same as the heights of kids that go to Indiana? Probably, okay? Um, so that is important to know, okay? Oops, sorry. So the answer is A. Like these are going to be the same, okay? They're trying to trick you here, like because the schools are the different size. These populations do not matter. All that matters is n, right? Our sample size is the same. So this smaller and larger than stuff just doesn't matter, okay? And it's not going to vary from sample to sample. So wrong-o. 8, the chipmunk population, okay, this is mu, and this is sigma. They weigh 9 chipmunks, so that's n, okay? So we've got 84, that doesn't help us. The standard deviation formula is this. So there we go, that's 18 divided by the square root of 9. That's 18 divided by 3, so that's 6. All right, so it's one of these two. And is it normal or not normal? Well, is 9 big enough? Is 9 greater than or equal to 30? No. So it is. It doesn't say not normal, it just says unknown, okay? But we do not know that it's normal. 9 is having you look on your cheat sheet down here in the bottom and doing a z-score for a sample average. So x bar minus mu and standard deviation on the bottom. Just got to piece it together, right? It's telling you all in adult males, okay? Here is mu with a standard deviation of 6, that's sigma. N is 5, okay? And then greater than limits you to this one, or this one, or this one, or this one, okay? So it can't be that one. And then the denominator, you can rule out this one and this one because that's not the formula, right? The formula is divided by the square root of 5. So then which way do you subtract? You do x bar minus mu on the top. So that brings you to C. 60 is the result of your sample. That's your x bar. Okay, number 10 is the same thing, but it's p hat minus p over the square root of p1 minus p over n. It says 53% of all adults, so that's p. And it says less than half. Okay, so that means it's got to be one of these two. Oh, that was nice. I can get rid of those because they're all greater than. And then between those two, I can tell pretty much right away this is not the right standard deviation formula. So you could just get rid of that one. So it is D. Free response. It says here for this one, we know that the distribution is normal. So that means we can still do these two questions. Just to flash ahead, that is actually why we're doing part C. Did we need to know the population of the eggs was normal? Yes, because if the population is normally distributed, then any sample of any size will also be normally distributed. And these situations, the sample size did not get to 30. So I need to know what was normal. All right. For both A and B, they're kind of similar. You're going to get a z-score for both scores. And in the first one, the standard deviation is just 5 because you divide by the square root of 1 because the sample size is 1. You can do your normal CDF button. Had a brain fart for a moment. So negative 0.5 comma 0.75, and that's where I got my answer. You can also use your green sheets. Just take your time, show your work. Letter B is very similar. It's just that now you're dividing by the square root of 12. So your standard deviation went from 5 down to 1.44. So now you're dividing by 1.44, which changes both your z-scores, which raises your percentage to 95. Already talked about C. Number 12. A lot of you did really well on A. If 20% of all the listeners are male, that will be the mean of the sampling distribution. This is the formula in the green packet, or the green cheat sheet. 0.20 times 0.80 divided by your sample size. So standard deviation of about 2.8%. Letter B, you can ignore that, is explain why we can use the standard deviation formula. On your cheat sheet, I had you write it there, right here, right? Why can we do standard deviation? We have to check the 10% rule to see if they're independent. So you could say the sample size was 200, right? 200 listeners. Is 200 less than 10% of all the listeners of this radio station? You could comment about that and say yes. You could also just take a more general approach and say every listener is independent of the other listeners. So you have to address independence in some way for part B. Part C, you're given the results of a sample. 50 out of 200 is your p-hat. So 25% of the sample were male. And you're going to get a z-score for it, right? The distribution is centered at 0.20 because that's what it's been historically. 20% have been male. And the sample came back at 25% way over here on the right. And you're going to get this percent to be 3.7%. So you take your 25% minus the center divided by the standard deviation. You're really taking these numbers that you got. This is how they usually work, right? Part A, you didn't do it for nothing. And you get a z-score of 1.79. Look it up in your green packet. There you go. So this result is significant because it happens less than 5% of the time. So it does look like changing adding in a male host has increased the number of males that listen. Last one. This is the population information. They're sampling to figure out how much money kids spend on books in college. Every dot, part A, every dot is one sample of 32 kids. They asked them how much you spent on books. And then from that sample of 32, they calculated the IQR. So this dot is one sample of 32 kids, and that sample had an IQR of 240. Then part B, I had you just take the 165 from up here. What is this minus this? Because it's Q3 minus Q1. 380 minus 215. So we know that the population, this is the value for the population. 165 is the value for the population, which leads you into part C. Is this unbiased? Is it centered at 165? And it is, because there were 50 dots. If I count in 50 dots this way and 50 dots this way, I get right here, which, look at that. That's at 165. So even though there's maybe more dots on this side, that's okay. It's centered where it should be. It is overestimating these 25 dots. It's underestimating these 25 dots. It is doing over and underestimates equally. So it is properly centered, so it is unbiased. All right, folks. Bye-bye.